Optical-pump Terahertz-Probe Spectroscopy. So will be presented by Jessica.
Brilliant. Thank you for the introduction. As you can see, I am not Ing. Unfortunately, she couldn't come here today because of her visa. She has recorded the talk, so we will put the recording on our website. So if you Google all things terahertz, you can watch her version of this presentation, which will be way better than the one that I'm going to wing now. So please do that. But we would like to show you our results on zinc phosphide thin films. And the reason we're interested in zinc phosphide thin films is because they're great candidates for solar cells. So our lovely collaborators in EPFL came to us and said we've grown some lovely, we think, monocrystalline zinc phosphide thin films, think being important, on indium phosphide substrates, and we'd like to know a little bit about their dynamics. Now, zinc phosphide is great because it's got a direct band gap at 1.5 electron volts. And that means that in the Shockley-Praiser limit, it's close to the optimal bandgap energy for solar cell operation. So it's a really good candidate for that, but its light absorption is also pretty good. It's got absorption coefficients on the order of 10 to the 4, 10 to the 5 per centimetre, and it's got quite long diffusion lengths. It's also not made out of any horrible lead things, sorry perovskite community, and it's earth abundant and non-toxic. So, could be a good contender, but can we get it to grow well, and what is its optoelectronic properties like? So we're going to use contactless probing, terahertz spectroscopy, and we're going to see if we can relate that back to some of the DC characterization of our solar cells. So we're using Optical-pump Terahertz-Probe spectroscopy. You can do this in both transmission mechanism and reflection. And we usually go for transmission. So we have an optical pump beam that's usually on the order of near infrared, so 800 nanometers, and then we're measuring the transmitted terahertz radiation and using electro-optic sampling to detect that transmitted beam. This actually was a little bit of a problem because of that indium phosphide substrate. We couldn't get a sufficient terahertz transmission through this. So if we wanted to look at it in that geometry, which is the same geometry that's going to go in the solar cell, we're going to have to switch away from being in transmission mode towards reflection mode. But in both systems and both ideas of this spectroscopy, we can still get ideas about carrier mobilities, scattering rates, carrier lifetimes, and surface recombination velocities. So both are going to be really good as a non-contact probe for that. But we have to bear in mind that when we're in reflection configuration, we need to be careful if our substrate is conductive. We also need to think that actually what is our probing depth? We're going to be more surface sensitive in this case, but it is a little bit easier for making those sample preparations. We've got our thin film directly on the substrate that it's grown, so we haven't changed anything to do with the growth of that thin film. So that's kind of one of the motivations for going forward to reflection mode. So we're measuring the reflected terahertz waveform, which you can see in grey here, and then we're photo-exciting our sample, and we're also looking at that change in the terahertz reflected beam. And that's in the darker line here. So we're getting 2D data, we're getting the full waveform, but we're also looking at different times after photo-excitation. And if we extract that, we can look at the decay. So we're going to show spectral data and decay data, but I'm mainly going to focus on the decay data today. So this is what a decay data looks like. This is showing that change in the terahertz transmitted or reflected beam. You can see this isn't my practice timings, I'll just keep running back. So you can look at that change in reflected signal as a function of time after photo-excitation, and that will tell you about the carrier lifetimes of recombination, but also you can look as a function of delay between your terahertz and gate beam, a function of frequency. So we're doing this in reflection, and we're also using an optical pump at about 750 nanometers. This is about 1.65 electron volts. So it's above band gap, so we should be generating electron and hole pairs.
There is a last question before we start our measurement.
This is her voice. I don't know how to make. Okay, sorry. Her voice is beautiful. You can listen to it on the website. So we did check that we were also okay with our assumptions of the thin film approximation. So we're actually using the full version of the wave equation to get to our conductivity that I showed you, and we've calculated with a Beer-Lambert law what the conductivity profile should be. And this is to prove that we are probing and dominated by the zinc phosphide and not that indium phosphide substrate. So you'll see that the indium phosphide substrate is negligible in what we're actually measuring, and using the absorption coefficient, we can say that we've got this Beer-Lambert profile. So that's going into our data analysis when we look at this decay data. So this is our decay data. You'll notice that it looks pretty flat. It's mono-exponential. Already looking at this, mono-exponential decays suggest to us that we have some monomolecular recombination. Automatically, I'm now thinking, is this really monocrystalline? We've got quite a lot of traps possibly, and monomolecular recombination here. So we went back to our collaborators and looked in a little bit more detail, and actually we do have polycrystalline samples. But by using this equation here and taking into account our absorption coefficient, we can convert those decays into carrier densities and start to fit to get those monomolecular, bimolecular, and Auger recombination out. And this is our fitting here that we've done on this data, and our bimolecular recombination constant that we've extracted matched literature for this zinc phosphide, so we're pretty confident in that, but we do have quite a large monomolecular term there. So that was actually really informative for our collaborators to go back and look at their growth process and see why we might have these defect states or trapping that could be contributing to that. We can also look at the peak of that decay and get an estimate of carrier mobility. There is some assumptions that go into this. We use the absorption coefficient, and we're also assuming that every photon generates an electron-hole pair. So this is going to be an overestimate of the mobility, but we've got some nice mobility values coming out. And we're trying to think about that solar cell operation. So we're focusing on the one where we've got the highest confluence here at the end, where we're getting mobilities on the order of about 100 centimeters squared per volts per second. And this is kind of in the range that we expect for this zinc phosphide thin film. The next step for us in our group is to look in more detail at the waveforms that we collected and the spectral data, so the difference due to photoinduced. And we have calculated what the sheet conductivity should be. Now, because this was a thin film, we were expecting to see a lovely Drude response, but you can clearly see that we have something that looks a little bit like an Lorentzian shape here. So the next step for us will be fitting this with the Drude-Smith model. We think we're having backscattering due to some of that polycrystallinity of thin films. So that's our next step here, but as you look at different times after photoexcitation, you can see that the conductivity is reducing, and also that crossing point that we see in the imaginary part in red is shifting as well. So that's giving us a little bit of an insight there. And we're going to look into this a little bit in detail about what kind of models we can fit to this spectral data to extract the scattering rates and relate that back to the carrier mobilities that we've got from the decay curves. But this is quite a nice study already in terms of looking at the mobilities and showing us about the dynamics in these thin films. And one of the strengths of this particular study for our collaborators was that we didn't have to change anything in the growth parameter. So we could look at it in situ on the substrate that they have grown. And the next future work for this is they're starting to grow on a graphene buffer layer. So we're hoping to look at those samples and use some of the knowledge that we've learned on the analysis side to look at them and try and do more kind of full device measurements here on this thin film. And with that, I would like to thank our collaborators, especially Anna von Roberta in Morales Group, in Bell for providing the samples, and also for the Warwick Centre and lovely James's Face over here for letting us use their gorgeous ultra-fast amplifier facility, and the CDT funding Ling, who is wonderful. She's actually the one on the bottom on the left there. So please do check her out. And if you go to our allthingsterahertz.com website, you'll be able to see her version of this talk. And thank you for listening.